All right, let's dive into a true classic, a problem you'll see all over the place in coding interviews, the threesome problem. Now, I know it can look a little intimidating at first, but trust me, by the end of this, we're going to break it down into a super simple, elegant puzzle. Okay, let's get into it.
So, first things first, what are we even trying to do here? The goal sounds pretty straightforward, right? We're given a bunch of numbers in an array, and our job is to find every single group of 3 numbers that adds up to 0. But there are 2 really important rules. First, the sum has to be exactly 0. And second, the triplets we find have to be unique. No duplicates in our final answer. That's key.
And that's the real puzzle, isn't it? How do we build something that's smart enough to find every single answer, but also clever enough to not give us the same answer over and over again? Well, let's start where most people would, with the most obvious approach. Okay, so whenever you're faced with a problem like this, the first thing that probably pops into your head is, well, why don't I just check everything? And that's the brute force approach. It's a totally natural place to start thinking, but for this problem, it's also a trap. The logic here is, well, it's simple. You just set up 3 loops, one nested inside the other. The first loop grabs a number, the second loop grabs another number, and the third loop grabs a third. Then you just check, hey, do you 3 add up to 0? You do this for every single possible combination. Easy to write, right? But what's the hidden cost?
The cost is time, a massive amount of time. This method has a time complexity of O of n cubed, or n cubed. To put that in perspective, if your list of numbers doubles in size, the time it takes to solve could go up by 8 times. In a coding interview with any decent-sized list, this is just going to be way too slow. So if we're keeping a scorecard, brute force gets a big, fat nope. It's basically a guaranteed time limit exceeded error. It's a trap because it feels like you're solving the problem, but you're not solving it efficiently. We need to be much smarter. And this is where the magic happens. The single most important thing you can do to crack this problem is one simple step. Sort the array first. Seriously, this one move changes the entire game. Just look at the difference here. The unsorted array on the left, it's just a jumble of numbers. Total chaos. But after we sort it, we have order. We have structure. All the negatives are grouped together on the left, positives on the right. This predictability is the secret weapon we're about to use. So what does sorting actually get us? 2 huge things. First, it unlocks a really powerful algorithm called the 2-pointer technique, which we're about to get into. And second, remember that pesky duplicate problem? Well, now that all the identical numbers are sitting right next to each other, spotting them and skipping them becomes super easy. So let's talk about this cool technique I love to call the 2-pointer dance. It's this really slick, really elegant way to find a pair of numbers that adds up to a target in a sorted array. It's awesome. So here's the setup for the dance. We've already sorted our array. Now we're going to loop through it one time, fixing one number at a time. Let's call it I. For each I, our problem basically becomes a simpler one. Find 2 other numbers that add up to the negative of I. And to do that, we set up our 2 dancers, a left pointer that starts right after I, and a right pointer that starts at the very end of the array. Now, let the dance begin. This right here is the heart of the whole algorithm. It's so smart. We add up our 3 numbers, the fixed one, I, and the 2 our pointers are on. If that sum is less than 0, it's too small. So how do we make the sum bigger? Easy. Since the array is sorted, we just move our left pointer to the right to grab a bigger number. And what if the sum is greater than 0? Too big. So we do the opposite. Move the right pointer to the left to get a smaller number. And what happens when the sum isn't too small and it isn't too big? It's exactly 0. Bingo, we found one. We've hit the jackpot. We add that triplet to our list of answers. It's this intelligent, systematic closing in from both sides that makes this so fast. But we're not quite done. There's one more detail to handle. Remember that other big rule? Our triplets have to be unique. Right now, our logic doesn't quite handle that perfectly. This is the final layer of polish we need to add to make our solution absolutely perfect. Let's look at a real example. Imagine we have this array. When our fixed number I is on that first -1, our pointers might find 0 and 1, and we'd get the triplet -1, 0, 1. Great. But what happens when our loop moves to the next -1? Our pointers could find the exact same 0 and 1 again. We need to stop that from happening. And the solution is this one beautiful, simple line of code. This is the key. Before we even start the 2-pointer dance for our number I, we just do a quick check. Hey, is this number the same as the one I just checked?
If it is, we already found all the answers for that value, so we just skip it and continue to the next one. So simple, so effective. So really, we need to handle duplicates in 3 spots to be safe. First, for our main fixed number I, like we just saw. But also, after we find a valid answer, we need to keep moving our left pointer forward until it's on a new, different number. And we have to do the same thing for the right pointer. This makes sure that if we have, say, -2, 1, 1, we don't add that same triplet twice just because there are 2 ones.
Okay, let's put it all together. Let's see why going from that brute force nightmare to this elegant 2-pointer dance is absolutely the winning strategy.
The final time complexity is O of n squared, n squared. So where does that come from? Well, the sort at the beginning takes O of n log n time. Then our main loop runs through the array once, that's n. And inside that loop, our 2-pointer dance takes at most n steps. So that's n times n, which is n squared. And since n squared is bigger than n log n, it's the one that defines our overall speed. A huge, huge improvement over n cubed.
So here's our final scorecard. Brute force, out. Way too slow. Now, there is another method using a hash set that's also O of n squared, but the duplicate handling gets really messy. You end up having to sort every little triplet you find just to check if you've seen it before, which is clunky. But our method, sort plus 2 pointers, it's fast, the logic for handling duplicates is built right in, and it's just clean. It's elegant. This is the solution that shows you really understand what's going on.
So if you walk away with anything today, let it be these key ideas. 1. Brute force is fine for a first thought, but always ask, how can I make this better? 2. Never, ever underestimate the power of sorting your data first. It can completely change a problem. 3. The 2-pointer method is a must-have in your toolkit. And 4. The details matter. Always think about those edge cases like duplicates. And that's really how you crack the threesome code. You take chaos, you create order, and then you perform this elegant little dance to find exactly what you need. So the question I want to leave you with is this. Now that you have this powerful pattern in your head, what other hard problems out there are just waiting to be unlocked by this 2-pointer technique? Thanks so much for tuning in.